Okay, so listen up for 1 sec, and then I'll let you get back to this. I did want to do a little review at the beginning, which was basically this sheet. So probably just as good I didn't hand it out yesterday. So we have 2 new people here who weren't here for yesterday. This is Damon and Adam. And if you guys want to chat after class, we can figure out some details about some stuff. Otherwise, any questions from the first class? Concerns? We're back for day 2, so looks like only a couple people left, but no big deal. You guys all have my email address too. So as I said yesterday, feel free to email me if you have any questions about anything. But let's do this. Let's look at you should have pages 1, 2, and then page 3 to this sheet. Try to do as many of these as you can, and then we'll go over it in like 10 minutes or something like that. And if you have questions, there was one that I goofed on. What was the one?
Oh, that was in the blue.
It was on the first page or second page?
Second page.
Second page.
Express each rational number as a decimal.
Express each rational number as a decimal. Which one did I mess up?
Number 3.
Number 3. OK, it was negative instead of positive. Thank you very much, Oliver.
Chris, can you borrow a calculator?
Yes, let me get those. I don't have, like I said, I've only got like 8. But I'll hand out as many I've got, or 10 or something. There you go. You guys share if you need to. Great, small. Which one was it? 0.5399?
Yeah.
0.5399. If it stops like that, it's pretty easy. You just count how many places you have to go from the decimal place and put it over 10 raised to that number. So 1, 2, 3, 4. What's 10 to the 4th? Right, 10,000. So it should be 539. I'm getting it wrong. 5399. I still got it wrong. There we go. 5399 divided by 10,000. Did I write 1,000?
So if it was 5399.0.
5399.0?
Yeah. So that would be 5399 over 1,000.
Nope. If it was, you mean if the decimal, if the decimal wasn't there?
Yeah.
Yeah, that's it. Well, it would be 5399 over 1,
Oh.
right? Because it's already an integer by itself.
Oh.
So you could do that. Number 10 is really mean. Sorry. Say again? Oh, did I not give you the third last page? Wait, I gave you one today. I didn't also give you this one? There you go. And that has the answers from the other page on it, too, that we did yesterday. OK, let's see. Oh, wait. Do it all together.
Drop the negative on the over 7 when you turn it to 20 over 35.
I did, thank you.
Yep.
So it's not going to, all my fancy stuff isn't going to work, is it? Oh, it will, it still will. Still will, almost. Let's see, negative 20 plus 14 is negative 6. And then,
Drop the negative on the 35 over 72.
no, I didn't.
And the negative 27 minus h, negative 35.
No, it should be negative 35 over 72.
Hang on, this is not right. I know that's not right.
So negative 35.
This should be negative 35 over 72. You're right, here. Thank you. Okay, so that's going to end, that is still going to cancel out there. Negative times negative is a positive. So we're good there. Going to be 6 over 72. And 2 goes into 6 3 times. 2 goes into 72. Did I reduce it on the page?
Reduce it by 6.
Oh, you can. 36, right? How about 1/18th?
112.
No, I'm a moron. 112. Thank you.
12 times 6.
Thank you. There we go.
The bracket, it should have been minus 27 plus negative 8.
Plus -8, which I turned into a minus. But you're right. Same.
That's the only thing that.
Awesome. Okay. Yeah, that was a mean one. I know, screwed it up. Good.
I did it. I can't do it the way you did it.
You what?
I can't do the math the way you did it. I have to put them on, stack them.
Stack them in. Stack which?
Like, I'm gonna explain it like this way. I can't do it that way. I have to stack them that way.
Oh, okay.
If I do it that way, I get.
Oh, that's not a bad idea. That's a good way to do it. I haven't seen it that way. But that looks like a good way to do it. Yeah,
I
that's
can't
cool.
do it.
That's cool. That's fine.
Throws me off.
No worries. No worries. You got everything else though? Almost?
Yeah.
Good. You got your own calculator. Okay. Anybody else need a calculator? Okay. How's it going? That was a tough one.
I just
My fault on
put
it.
28 because I was thinking 7 times 4, but it was
Oh.
5 times 4 is 20. That's why it's
Oh, yeah, okay. I will try not to ask you a hard one like that on test.
You are?
No, I don't want to. Well, what's the point really? I know you can do it. It's just a matter of getting like getting little signs and things wrong, and I don't know the point of that. Couple people.
But it's the same principle. So you just
How are you guys doing on yours? How you doing?
Oh, I'm doing.
This takes a while. I know this last one's a tricky one. Okay. Can you see the board from over there?
Oh, yeah, I can see perfect.
Okay. Oh, sideways. Okay.
For addition and subtraction, you have
Is that a negative 72? What happened to the 6 over 72? Because you got negative 6.
So here's what I did. I was sneaky on this one. See how the 35 is on the top here and on the bottom here? I canceled them out, which technically you can do that. We didn't really talk about it, but made it easier in the end to reduce it, although I still messed it up. Negative 6 times negative 1 gives you a positive 6. Because when this cancels out, this becomes negative 1. Because you can only cancel the absolute value part. Yeah. Okay, I think most people are. Sorry, are you still working on that one?
No.
No worries if you are. Tell you what. Here's what if you haven't seen this one, two things I would mention about this. I will not give you a hard question like this on a test. This was just kind of, to show you a difficult one, I guess. And that was point one. Point two is I made about, 5 mistakes on this one when I was doing it. So don't worry about the fact that you might make mistakes on these. Yes, it's about practice, and yes, it's about taking time. But really, this is just mean. Because you could probably do this in your calculator pretty quickly if you needed to. And in real life, you're not going to see too many questions exactly like this. OK. Anybody want me to leave this one up here while you look it over? Go ahead. Or you want me to go through it step by step? I'll do that. I'll go through it. And then you can keep working if you don't want to pay attention if you already did this one. I wrote it. I think this is exactly like it was on the sheet. OK. First thing we do is the parentheses, right? So what I did on here, I looked at these parentheses, and Christine said, hey, how do you deal with this? This is a good question, because we didn't go over it yesterday. Forgot. When you do a minus, when you subtract a negative number, you can call it a positive number, and you can say, I'm adding a positive number. So I just took that out, and then when you do that, you don't need the parentheses anymore. That was kind of step one. I actually did the same thing over here, although I probably didn't need to. Probably should leave the positive plus, leave the additions. So what I did was I said, oh, this is going to be minus a positive value. And that's what I did here. But it really doesn't matter in the end. It probably makes it easier. You probably want to swap it in the end anyway. So don't. I did that, but it doesn't really matter. But that was how I got rid of the parentheses. Really, this is negative 3/8 plus negative 1/9 or minus 1/9. Then I got down here, and I made these in little tiny numbers just so it stayed roughly the same. When you're adding two fractions that have different denominators, you have to have a common denominator. The easiest way to do that is to multiply this one by this one and multiply this one by this one on both the top and the bottom. So that's what I did here. I said 7 times 5 will be equal to 5 times 7 on the bottom, so the denominators will be the same, the 35. And then I said I have to do the same thing on the top here. So this one times 5, and this one times 5. So negative 4 times 5 is negative 20. And here, 2 times 7, because it was 7 down here, is 14. And that's where I got negative 20 plus 14. It's the exact same concept over here. 8 and 9, you can just multiply them on both sides. The 8 times the 9 on both the top and the bottom here. And the 9 times the 8 on both the top and the bottom here. Make sense? If it doesn't, that's OK. We can go over it slower either now or on Thursdays. Everybody still OK with Thursdays? Evenings? OK. And that is not mandatory, by the way, just so you know. Completely not mandatory, but recommended if you're having troubles. OK, and then anyway, now I have the common denominators here. And I've multiplied the denominator, the numerators as well. Negative 27 plus a negative 8. When you're adding two numbers with the same sign, you just add them, and then the sign is the same. OK, so it's going to be, in this case, negative 35. I moved this whole part down here because I ran out of board space. OK, negative 35 over 72. And this one ended up being negative 20 plus 14. If they're different signs, you subtract the absolute values. And then the sign is the one of the bigger one. So 20 minus 14 gives you 6. It's negative 20 because it's the biggest one. Negative 6 divided by 35. I did a little trick here, which you don't have to do. But if two numbers, if you've got A over B times B over C, the B's actually can just cancel out, because it'll really be AB over, if you want to do it this way, CB. And those two are going to cancel out because it's like the same number over itself. So I just canceled those out, which made it easier to reduce in the end. You don't have to do that. You could have done negative 6 times negative 35 over 35 times 72. Then you would have had to reduce a little bit more.
Can you reduce the 6 and the 72?
You can. If you want to do that, you absolutely can. It doesn't matter to me. When you do it is fine. It's just one more step to do somewhere. OK. All right. Anybody have any questions on this long one? OK. How about the other one? Is it OK to erase this one now? Not yet? I'll wait.
If I have to see it, then I'll do it.
Whoops, sorry, William. Well. Who has another one that you want me to go over? You guys are good on all the other ones? If you are, that's cool. We can move on. Any specific ones? I'm open to do any of them.
Can you do one more for the express or repeating decimal?
Yes. Which number would you like?
Just do one again.
Just do any?
Yeah.
The repeating one?
Yeah.
Okay, I will. Will, are you good with this? Okay. All right, I'm going to erase this. Okay, so Oliver says, let's do a repeating decimal one. Let's do kind of a medium tricky one. I won't do a hard one. And by the way, I won't give you any of the hard ones where it'll always be just the numbers repeating after the decimal. You won't have to do one that has a weird thing after the decimal. But let's pick, give me, I don't know, 2 digits. 81? That's like on the sheet, right? We can do 81. It doesn't matter. 50, okay, we'll do 56. 56 repeating. You can write it that way, right? Which is how I wrote it on the board. OK, 56 repeating. What's the first thing we said we did with this? X equals the number, right? So in this case, 0.5656 dot, dot, dot. OK, then what did we do? We counted up how many digits repeated. In this case, there were 2 repeating digits. So we're going to multiply by 10 raised to the 2, which is 100. OK, so we're going to say 100x equals 56.5656 dot, dot, dot. And then what do? Subtract them. OK, so that's going to be 99x. Because if you have 100 x's and you subtract 1 x away, you're left with 99 x's. OK? And then this is going to be all 56.5656 minus 0.565. All this is going to cancel out and go away. So you're left with 56. And now you divide both sides by 99. And you end up with x equals 56 divided by 99. And you can reduce that if you can. I don't think you can reduce that one. But if you wanted to, you could. I'm not going to take points off if you don't reduce on tests. OK? Homework, they might. But just if it says you didn't reduce it or whatever, it's fine. OK, you might not have gone over this in last class. Not sure you did. We can talk about it later if you want. Any questions? Any more questions on that one?
No, I'm good.
OK, this one's not too bad. I don't think. This is just remembering the steps. Yeah. OK. Yeah, I think I talked to Elliot and he said don't do this one. But I did anyway because I thought you guys could do it. So, all right. Any other questions on that? Any of those sheets? The homework's very much like what you just saw, correct? Homeworks are a lot like that stuff. So, if you can't do the sheet, then you might have some trouble with the homework, but that's fine. By Thursday, you'll be able to come in and get some help if you need it. OK. All right. Let's go on to. So we have done a few different types of numbers. We did the natural numbers, which started from what? 1, 2, 3, 4, 5. We did the whole numbers, which started from 0, because 0 is one of those weird numbers that it took 3,000 years to figure out when people started doing math. 0, 1, that's the whole numbers. Then we talked about the integers, which includes all the negative numbers. Okay. Then we talked about the rational numbers, which included what? Fractions and decimals that are either terminating or repeating. Okay, so that's where we ended up yesterday. Today, we're going to start talking about irrational numbers. Okay, and if you think that that's the last of them, there are other ones, but I think that's the last ones we're going to talk about. Anybody remember talking about imaginary numbers in like high school or whatever? Yeah. Do imaginary. We're not going to do imaginary numbers in here. They're definitely a little crazy. OK. From yesterday, OK, we had rational numbers were a over b, and they either terminated or repeated. OK, just remember that. Rational numbers either terminate or repeat when we write them in decimal notation. Okay, so you could have 0.723. That's it. Okay, that's a rational number. 0.723 0.333 dot 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 dot, that's a rational number. Why? Because you can pick out something that repeats. OK, I told you yesterday we talked about one number that is not rational, that doesn't repeat. What was that special one? Pi. OK, so there's an example. Whoops, that's not how you draw pi. Whoop, I did it again. There we go. Whoop, there we go. Pi is a number that never repeats. OK, it's called an irrational number. It just happens that it becomes an irrational number. Where do we see pi mostly? Do you guys remember from maybe geometry class or whatever? Circumference, right? If you take a circle and you know the diameter of the circle, right? The circumference around it is actually pi times the diameter. Okay? And it turns out that you can't get that number exactly. If you built a circle that was exactly, say, 10 centimeters across, and you tried to measure the circumference around with a ruler or whatever, you couldn't get it exact. Right? The Greeks figured this out a long time ago. I think it was the Greeks. And it boggled them. Right? It was crazy. And that's because pi is irrational. I-R-R-A-T-I-O-N-A-L. Irrational. OK, so that's one example. OK? There's another here. See if you can figure if this is irrational or not. 0.2322 2223 dot dot dot. Is that a rational or irrational number? It goes a 2, then a 3, then 2 2s, then a 3, then 3 2s, then a 3, then 4 2s, then a 3, etc. What do you think? I'll give you a hint. We're talking about irrational numbers. Right? There is a pattern here, right? But can you put a bar over any of this and say that that's going to be repeated each time? No, because the next time you have 5 2s, and the next time you have 6 2s, we could figure out a way to tell somebody how to write this number out, right? But that doesn't mean that it's a rational number. This is not a repeating number simply because you can't find a section that always repeats. That's part of it. So numbers like that, also irrational. OK? There's other irrational numbers. I think I mentioned this the other day too. The square root of 2 happens to be irrational. OK? And I don't even know what this is, like 1.71 something something, but there's no repeating part to it. You can't ever find a pattern that always repeats. OK? Same with pi. It's a very similar number to pi. OK? So those are examples of irrational numbers. 3 point, what was pi? 1 4 1 5 9 2 6 5 3 5 9 something 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 something. I don't know when I remembered that, but people do contests where they memorize pi to like hundreds of thousands of digits. Right? That they figure out like a mnemonic, like 3 is like your elbow, and then they remember, oh, I go from my elbow to 1, which is my like finger, and my elbow to my finger. They do all these mnemonics. And they memorize like thousands and thousands of decimals, and they just sit there and they like just count them out, I guess. And somebody grades them. Somebody just goes, yep. And then when they miss one, you're done. So, but kind of crazy. Anyway, those are irrational numbers. Now, even though they're irrational, they're still perfectly good numbers. Like they still fit on the number line. Okay, so if we remember the number line from yesterday, right? If this is 0, 1, 2, there we go, 3, 4, pi is somewhere right about there. Right? It's still on the number line. Okay, if we were to get into imaginary numbers, we'd find out that they don't even fall on the number line. But all the irrational numbers do fall on there. Okay, and you can always get a little bit better. If you had a microscope, you could like zoom in a little bit more and go a little closer to where it exactly is, right? But it's on there somewhere. But it's not, it's not one of these other weird, or not one of these other repeating kind of numbers. Okay. Questions on that? All right. So a lot of times, most of the irrational numbers that we see won't be those weird ones like the 0.2332, 333, whatever. The ones that we'll see most of the time are going to be these square roots. Okay? hopefully all the calculator, if you have your own calculator, it has a square root button, because that's going to be very necessary for this class. Square roots a lot of times are irrational. Not always. We talked yesterday, the square root of, say, 25 is a rational number, because you can figure out where the, you can turn it into, this is going to be 5, well, it's going to be 5. It's going to be the square root of 5 times 5. And the square root of a number is a number that when multiplied by itself gives that number. Okay, so that's what the definition of a square root is. Okay, the principal square root of a number, of a non-negative number, because you can't do this, by the way. This is where we get into imaginary numbers. You can't do the square root of negative 25 anywhere on the number line, because you can't find two numbers multiplied together that will give you negative 25. And we can show that really easy, right? What is, let's use this example. OK, 5 times 5 equals 25. What's negative 5 times negative 5? No, not negative 25. Also 25, right? Yeah. So if a number, and numbers can't be anything other than positives or negatives, right? So if you have two positives or two negatives, they will always, when multiplied together, give you a positive number. Should be parentheses there, right? So you can't find a number multiplied by itself that gives you a non-negative number. Or sorry, a negative number. You can't find it. So that's why we can't. That's why this has to be. That's why it has to be a positive number. Okay. So let's look at this. How about this one? Square root of 36 is what? 6, right? Square root of 36 is 6. Okay, which means 6 times 6 equals 36. Okay. So far, so good. Square root of 49? 7. OK, a lot of these you guys know from like the times tables, right? Square root of 3? 1. It's not 1.5. You'd think it would be. Like you might think it is. But that would be adding two numbers together, right? It's actually, you could do this on your calculator, well, I'll put approximately, that little squiggly equals sign, 1.73205 dot, dot, dot. It's another irrational one. Happens to be irrational. Okay? So what we're going to end up doing over the next few minutes here is we're going to figure out how to get numbers into a form where all that's left are these numbers that you can't reduce anymore, and those are the ones that are going to be irrational. Okay? And we'll get to those. We'll get to that when we do some more of the things. Anybody know why they're called square roots? Why square? A number squared is a number times itself. That's kind of a tautological definition, right? It's kind of like you're saying, well, it's called square because we call it square, right? But no, if you look at it, some numbers are what we call perfect squares. If you drew a box like this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 boxes this way, and then 1, 2, 3, 4, 5 this way. Let's see if I can get there. There we go. Boom, 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 boom. Hopefully I did that right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I did do it wrong. There we go. 1, 2, 3, 4, 5, 6. There we go. All right. 6 by 6. It actually makes a perfect square. That's why we call it a square number, right? Or the square root, because when you multiply 6 by 6, they're the same number this way and this way. Kind of cool. OK? All right, one thing about square roots. OK? The square root operation and multiplication do this thing we call commute, OK, which means we can combine them. Here's what it really means. OK? If you have A and B, and they're both non-negative numbers, non-negative, two non-negative numbers, A and B, if you have the square root of A times B, that equals the square root of A times the square root of B. This is how we're going to get this so that we start reducing these to the answers that we were interested in. Okay? So let's take a look at this. Okay? Square root of 36 times 4 equals what? Well, it equals the square root of 144, right, which is 12. Okay? But you could also say that it equals, which equals 12. I'll write that there, which equals 12, because you can just multiply those in there. Or you could say that it equals the square root of 36 times the square root of 4. And we know that the square root of 36 is 6. And we know that the square root of 4 is 2. So that also equals 12. See how that works out? Okay. Some of this stuff might be like dredging up old stuff, or maybe you never saw it before. But that's the way we can do this. So it's going to make it so that we can get these down. You got that? Got how that works now? This one, all we did here when we said, well, 36 times 4. Well, we can do that because it's under the square root. And then it ends up being that. And we know that square root of 4 and 44 is 12. Okay? You should practice this on your calculators, too. Some calculators, you'll have to do the little square root button first, and then the number, like 144. Other ones, you do 144 first, then you hit the square root button. And then it should give you 12. So make sure you know how to do that on your calculator. Practice it if you don't. Okay? And if you can't figure it out, bring it to me and we'll figure it out together. Questions? OK. All right. We got to learn how to do this simplification of square roots. Simplify them into that form that I was talking about before. Okay? What you're doing is you're removing from the square root those perfect squares that we talked about. So if you can get a number into a form where there's a perfect square, like 36 or 49 or 64 or 4 or 16 or whatever, then you can bring that out because you can take the square root of that part. Okay? You can factor that out, we call it. Okay? So here's an example. Square root of 108. And again, this takes a little bit of guessing and checking sometimes. Because if I looked at 108, I wouldn't necessarily know that that happens to be the product of, in this case, square root of 36 and 3 times 3. 108. Do 108 on your calculator. Hopefully that's 108 divided by 3 should give you 36. Yeah? So now if we know that that's that, what can we do to this? We can say that equals the square root of 36 times the square root of 3. We know the square root of 36 is 6. So this becomes 6 times the square root of 3. And this is how we'll write it. It's kind of like the square root sign acts as a little parentheses in there for you. Okay? So this is the same as this. By the way, you can also go backwards. If you want to move the 6 inside there, you have to do what to it? If we're taking the square root to move it out, you have to square it to get it in there. So that would be, you would have to say 6 equals, you square it, the square root of 36, times the square root of 3, and then you go backwards, and you end up with square root of 108. We're not going to do too much going backwards. Most of the time we want it in this form instead of this form. OK? All right. Let's see. There's another way to do this one. We could also, if you didn't know that it was, let's say you didn't know that it was divided by 3. What's 108 divided by 2? Is it 54? OK, so then this would be the square root of 2 times 54. We don't know any perfect squares yet there. Let's keep doing that. What's this going to equal? What if we do 54 divided by 2? 2 times, what's 54 divided by 2? 27. 2 times 2 times 27. OK? Right? OK. And then let's see. What else is left here? If we do 27, well, by the way, you can do this now. If they've got 2 times 2, you've got square root of 4 times 27. OK? And that equals, what's the square root of 4? This is going to be square root of 4 times the square root of 27. So now we've got 2 times the square root of 27. Uh-oh, I'm running out of board. Let me move up here. 2 times the square root of 27. 2 times the square root of 27. OK, what goes into 27? 3 and 9. So now you've got 2 times the square root of 3 times 9. Aha, there's a perfect square. 2 times the square root of 3 times the square root of 9. That becomes 3. 2 times the square root of 3 times 3. Well, what can you do to these two? You can multiply them together, right? So 2 times 3 is 6 square root of 3. Is that what we had before? It is, same thing. So a little more work if you didn't know it was that way. I know, that was a little bit more work. That was a bit fast. I went a bit fast on that one. We'll practice this. We'll practice it. You'll get it down. OK. All right. All right. Let's try another one. How about this one? Square root of 4 nines, the square root of 490. What's an easy thing that goes into 490? 7's not bad. Or 10, right? That's probably even easier. Square root of 49 times 10. And then do we know what goes into 49? Christine said it earlier, 7, and that's a perfect square. Aha. So now we can say square root of 49 times the square root of 10. OK? And square root of 49 is 7 square root of 10. What goes into 10? 5 and 2. Are any of those perfect squares? No, you can't do anything more with this one. Yeah, can't do anything more with this one. This is an odd one because the square root of 10 is actually an irrational number. But you wouldn't think it because, hey, it's 10, and 10s are always kind of like easy to work with, but not in this case. Square root of 100 is a rational number. It's 10, right? Because 10 times 10 is 100. The square root of 1,000 is irrational. You can't do something times can't do an integer times an integer to get 1,000. 10,000 you can, but yeah. So it gets a little weird. OK. We'll practice a couple more of these as we go along here too. Let's see. OK. If we did this, if you can multiply, remember you can multiply inside of square roots. Square root of 3 times the square root of 4, OK, gives you what? Square root of 12. OK? And now we would want to reduce that, which ends up being 2 square root of 3, because you kind of would get it back into this point, too. So that's probably not a very good example. But we can do that. How about square root of 15 times the square root of 3? Square root of 45. Can we reduce that? How are we going to reduce that? Yeah, this is going to be equal to the square root of 5 times 9. Which one of those is a perfect square? 9 is. Equals square root of 5 times the square root of 9 equals 3 times the square root of 5. Got it? Good? OK. Oliver and Martin, you guys got it? Or you want me to do another example? You got it though now? OK. OK. Just let me know. I'll be happy to go over any of these other ones. So multiplication works this way. Turns out division works this way too. Division's a little bit weird because for a long time, and we're going to do this too just because it's kind of one of those things that people have done for math and it makes things a little easier. But because of calculators, you probably don't need to do this anymore. But when we do division, but division works the same way. OK? So if you have two numbers, a and b, and remember, if a and b are non-negative, and I'm going to add something here, if b is not equal to 0, hey, what did we say? Why did I put not equal to zeros before yesterday? What do we make sure we're not doing with zeros? Dividing by zeros. So guess what? We're going to divide by b, right? If you have square root of a divided by square root of b, OK, this equals the square root of a divided by b. And if b was 0, then we'd end up with something divided by 0, which is bad news. Not good, not a good thing. OK? So in this case, we're going to make sure that b is not equal to 0. But this is what you can do to combine these two, OK? So let's try this. Square root of 108 divided by the square root of 3. OK? That equals the square root of 108 divided by 3. You guys doing all this in your head? That's cool. I can't do it in my head. What's 108 divided by 3? 36. Square root of 36, which equals 6. Okay? So that's not too bad. And you wouldn't necessarily know it. You wouldn't necessarily know that this divided by this gives you a nice rational 6. Okay? Whoops, sorry. 36 equals 6. There we go. I'll leave that there. And this was 108 divided by 3. There we go. All right. So let's do another one. Square root of 90 divided by square root of 2. What's 90 divided by 2? 45. What goes into 45? 9 and 5. So this equals the square root of 9 times 5. Sometimes, I know on homeworks and things, or on tests and things, you can skip some steps, but I'll try to write out all the steps if we can. Square root of 9 is 3, so that's going to be 3 times the square root of 5. Okay? And you, again, divide that by that, you wouldn't think, oh, it's going to end up being the square root of 5 in there somewhere. Wouldn't necessarily believe that, but it works out that way. OK. Any other questions? Can I erase this one now? Good? OK. All right. Any questions on this at all? No? If you add and subtract, remember how adding and subtracting fractions got a little weird, where you have to do common denominators and things? 4 times the square root of 3 plus 7 times the square root of 3. Think of those as kind of like the common denominator here. Even though it's not a denominator, it's under a fraction. Think of it like that. These two numbers, we can add just the parts that are out here. It's kind of like saying 4 somethings plus 7 somethings. Well, that gives you, what, 11 somethings, right? So 11 square root of 3. OK? How about this one? You do not add the 3's. It's like the common denominator thing. It's almost exactly like that. OK? And again, it's because you can't, it's because if you think of this in kind of an abstract way of something, even though it's something, can you add 4 apples plus 5 oranges and like say that they're 9 somethings? No, I mean, OK, pieces of fruit, but you can't, we could say this is, you can't do that in this case. Bad example, I guess. 8 times the square root of 2 plus 5 times the square root of 7. What's that? Yeah, you would try to make, you could try to do that, but we're not even going to worry about that, because that would probably make it more complex. You don't even worry about that. What you do is you say, I'm done. I mean, that's it, right? Because you can't add two things like that that are different, so we're just going to leave it like that. That's as minimal as we're going to care for these kinds of ones. So if you ever see that, something like this, just say, hey, I'm done. All right. You can do subtraction as well. 4 times the square root of 5 minus 6 times the square root of 5. Are those two the same square roots? So you can do the subtraction here. This is going to be what? Negative 2 times the square root of 5. I'll do it like I did yesterday. Some of you guys will go negative 2 times the square root of 0 or something. And I will take my red pen, and I will go boop, right? Because that's not right. Don't just learn the rules correctly on this. OK? You do not subtract the inner parts there. It's going to take a little time to kind of remember that, but when you're practicing these on the homeworks and things, remember, if you're trying to add and subtract things with radicals in them, you just leave the radical the same, -2 square root of 5. Okay? Questions on that? All right. Tell you what, let's take a break, and then I'll put one on the board to do when you get back. Okay? Okay. So I put one on here that we hadn't seen before. Let's see if we can figure this out. I know I said before that problems in this form, you can leave them, but that's only when these are reduced all the way. So can we reduce these radicals a bit more? Sure we can. 4 times the square root of what goes into 8? 4 times 2. What's that?
I thought that was a 5.
Which was a 5?
That number.
This one?
Yeah.
Oh,
Yes.
sorry. Nope, it's an 8. You'd have been right if it was a 5. OK, so can we take a square of one of these? Square root of one of these?
4.
Yeah, the 4, so that's going to be 2. This means times, by the way. Boom times boom. So we can do 4 times 2, because the square root of 4 becomes 2. So this is going to be 4 times 2, which is 8 times the square root of 2, minus, OK, what is 7? Sorry, what goes into 18? 9 and 2. What's the square root of 9? 3. 3 times 7 is 21 times the square root of 2. Now do we have the common radical here? So now we can do this. 8 minus 21 gives you -13 square root of 2. Had you done that one on your calculator and it just gave you that? Oh, OK, good. OK. So that's how we do these problems. Okay? All right. Do you want to work on the first couple pages of this thing while we're listening to colors?
Yeah.
Yeah, OK. You need a calculator for these ones, for some of them anyway. Well, you know what? This is only to practice using your calculator, I think, 3 and 4. But OK. Let's see. This is square root of 80. Here, I'll do this. I'll do number 6 on the board here. Square root of 80. OK, maybe I wrote down the wrong answer. Square root of 80. So what goes into 80? 10 and 8. OK, so 10 times 8. Are either of those perfect squares? No. Can we do that one more? Sure. 2 times 5 times 8. Any of those perfect squares? No. Is there anything else we can do? We can turn that one into, like, there's factors of this one still, right? Square root of 2 times 5 times 4 times 2. Are there any squares in there? 4. OK, so we'll get rid of that. OK, so we could say now this is going to be 2 times the square root of 2 times 5 times 2. Let me write it like this: 2 times 2 times 5. What's 2 times 2? 4. Is that a perfect square? It is. So we can get rid of that one as well. So now you can say 4, square root of 4 is 2. 2 times 2 is 4 square root of 5. Is that what I had up here? Yeah. So that's how we do that. I kind of went one step too far, but sometimes that's the way you do it. The other way to look at it is, what's another factor of 80? You might not know this. 5 times what? 16. Is that a perfect square? It is. So we're going to move that out. Perfect square, so it's 4 times the square root of 5 is a little easier. We went through a big long one, but we just went down a wrong path. That happens sometimes. Still ended up with the same answer, just a little trickier. Yeah. So I just would, you wouldn't have necessarily thought 10 sounds better to divide this by. 5 actually was a better answer to divide by, but it isn't. In the end, you should get the same answer. Just a little tricky.
Can you do the square root of 75?
Sure. What goes into 75?
5 times 15.
Square root of 75. OK. That equals, we could do 15. 25 is probably a better choice, but let's go down your route and see. What'd you say? 15 times 5? Is that true? 15 times 5 is 75? 15 times 5, 5, 2. Yeah, it is. OK. OK, so let's see. What goes into 15? 3 times 5 times 5. Are there any perfect squares there? Well, there kind of are. 5 times 5 is actually a perfect square. It's 5 times 5. Right? So I would probably do this. We could look at it, like Chad says, just look at it and go, oh, that's the perfect square. But I would probably do it like this. 3 times 25. Oh, 25 is a perfect square. Right? It's kind of adding a step, but that's maybe the way you think about it. What is the square root of 25? So it's going to be 5 times the square root of 3. Yeah. A lot of times math is about seeing things that you recognize. And sometimes it's hard to do that. Like I wouldn't have necessarily, I might have tried to do that too first. And then I would have gone, oh, I don't, well, if you keep breaking this down, you'll eventually get to the right answer. Yeah. Question?
Can you do number 11 right now?
Number 11. We haven't tried that yet.
All right.
Give me a minute. Unless you want me to do it right now.
No,
I'll give you a hint. This one's what? What is 11? It's 7 divided by square root of 27. This is what's called rationalizing the denominator. We're always going to try to get the bottom to not have a radical in it. Here's how you do it. You multiply by some number divided by some number that equals 1. What times itself will give you 27? So if we do this, then what does the bottom become? What is the square root of 3 times the square root of 3? Any idea? Let's use a better example. Let's do a better example. What is the square root of 25 times the square root of 25? What is the square root of 36 times the square root of 36? So the square root of a times the square root of a equals, nope. The square root of something times itself is always going to give you that number back. Okay, so what's the square root of 27 times the square root of 27?
7.
What was the square root of 36 times the square root of 36? What was the square root of 25 times the square root of 25? What was the square root of 27 times the square root of 27? It's the pattern. That's the pattern.
It's weird.
It is a little weird, isn't it? Although, yeah, it's weird. But that's kind of the definition of the square root, a number times itself. Like, gives you the number. But inside the square roots, well, if you do enough examples, you'll see that it works every time.
Yeah.
You could do it this way. You could say square root of a times the square root of a equal. You can move it inside like we were talking about earlier. Equals the square root of a squared. Well, the square root of any number squared is just the number. Yeah. So anyway, back to our little problem here. If we happen to multiply the top and the bottom by a number that equals 1, we can do that. Then this becomes 27 on the bottom. This becomes 7 times the square root of 27 divided by 27. Can we reduce that some more? What goes into 27? 3 and 9. Square root of 7 times the square root of 3 times 9 divided by 27. So then we're going to move this outside. 3 times 7 is 21 times the square root of 3 divided by 27. Does anything go into 21 and 27?
Yeah, no.
3 goes into 21 7 times. 3 goes into 27
Right.
9 times. So this is going to be 3 goes into 7 ninths times the square root of 3. I think that's the answer. Let's see. Don't worry. If I was just doing that to preview for a couple people. Where'd the answer sheet go? Let's see. What's 11?
7 square root of 3 over 9.
There you go. 7 square root of 3 over 9. Okay, good. We're going to redo this. So good little like preview of what we're going to do in a minute. What's that? I will not erase it. If you've gotten on to 11 and don't know how to do it, do not worry. That's the next thing we're going to do in about 2 minutes. Does anybody have any questions on 1 through 10 at this point? No questions on 1 through 10? Okay, good. Multiply and then simplify. Good. So let's see. Square root of 50 is perfect. Yeah, that's perfect. Good job. Okay. All right. Let's do this. I'm gonna go over exactly what I just went over with a couple people here. So this is back to the actual new stuff. Okay. Can I erase this now? Okay. All right. I want you to do something on your calculator. This is going to be a little tricky because sometimes it's tough to get this on your calculator. 3 divided by the square root of 3. So on your calculator, you're probably going to have to type some buttons like you're going to have to type 3, and then the divided by symbol, and then some people will type a little square root button, and then 3, and then enter. Other people might have to type 3 divided by 3, the square root button, then enter, or equals. Okay? But somebody read off what they got when they tried that, and I'll tell you if it's right or not. 1.732 ... some long. Okay. Do just the square root of 3 for me. Isn't it the same number? Interesting. The square 3 divided by the square root of 3 actually equals square root of 3. Oh, that's an interesting one. Okay. What we are going to try to do is the following. We're going to do this thing called rationalizing a denominator. Rationalizing a, or the, denominator. When we say we're rationalizing it, that means make it a rational number. Means get rid of any radical signs under there. Just get rid of them, okay? We have a special way of doing this, which involves something that ends up looking like this. But I'll write it out exactly. We'll do this example exactly. Okay? Can you multiply any number by 1 and get the same number? 10 times 1 equals 10. 104 times 1 equals 104. Any number times 1 equals the number. Good. Can you divide any number by itself to get 1? 6 divided by 6 equals 1. The square root of 3 divided by the square root of 3 equals 1. 22.5 divided by 22.5 equals 1. Using those two facts that we just talked about, multiplying anything by 1 leaves it the same, and dividing anything by itself gives you 1, we can do the following. Can I multiply 3 divided by the square root of 3 by 1 and know that I've still got the same number? Yeah? OK. Can I say the square root of 3 divided by the square root of 3 equals 1? Can I then say this number times this number has to mean the same as just this number by itself? You get those steps? No? Some people are like, no. Some people are like, yeah, no, I don't get it, but I'm just going to say yes so that I'll let you go on. One last time. Is square root of 3 divided by square root of 3 equal to 1? is any number times 1 the same number? So does that mean that if I multiply this by this, I will really have the same thing? OK. If we do this, watch what happens. The top we can multiply together to get 3 times the square root of 3. The bottom we can multiply together. And I didn't realize that this was a tricky concept, but it turns out it is. What is square root of 25 times the square root of 25? It equals 5 times 5, which is 25. What is the square root of 36 times the square root of 36? 36. What is the square root of 3 times the square root of 3? It's the same exact pattern. It's 3. Okay? You could do it this way. You could say square root of 3 times square root of 3 equals the square root of 3 times 3, which is 9. Well, what's the square root of 9? 3, which is exactly what we had there. Okay? So just if you don't want to like, if that's like warping your brain too much to go, oh my gosh, it does it. Just remember, if you take the square root of something times itself, you end up back with that number again. Okay? Christine's looking at me like my head's spinning.
It doesn't do that on the calculator.
You probably have to do parentheses if you're going to do it on the calculator. What did you type in your calculator?
Square root of 3 times
Square root of 3 times the square root of 3 should give you 3. What did you get?
I got like 2.2 something. But I saw what happened. That was wrong.
Yeah, you might have to put an end parentheses if you forgot to put. Sometimes some of these calculators, they will, when you type the square root button, it'll do a little square root with like a parenthesis in there. And then if you did 3 and you tried to do another times square root, you could do times square root. It would still be underneath this full square root. Not a good thing. You got to remember to close out parentheses if it puts it in there. So square root of 3 end parenthesis times square root of 3 end parenthesis equals 3.
I need to put the end parentheses.
Yeah, that'll do it. OK, now back to where we were. So we've got, on the top, we've got 3 times the square root of 3. What did we say square root of 3 times square root of 3 is? 3. Now do we have a number in the bottom that is rational? We do, but what else can we do? What's 3 divided by 3? 1. So this equals the square root of 3, which I asked you guys to do a couple minutes ago, and you all went, wow, it's the same number. It is the same number. This example ends up canceling a lot of things out, which is kind of cool. But watch when we do one that doesn't cancel itself out. OK? All right, let's see. Here's an example. 8 divided by the square root of 5. We'll get to that. Is that number 11? Yes. We'll do that one in a minute. Let's do another example like this. Then we'll do number 11. How's that sound? 8 divided by square root of 5. What did we say we multiply on the top and the bottom here?
Square root of 5.
Square root of 5 divided by square root of 5, which equals 1. So we know we can multiply by it. Square root of 5 divided by square root of 5. What's 8 times the square root of 5? 8 times the square root of 5. Can't do anything with that. And then what's square root of 5 times square root of 5? 5. There's your answer. Because we can't do 8 divided by that. 8 divided by 5 doesn't give you any other fraction. You can leave it like that. Okay? Let's do a slightly different one. Let's do the square root of 4 divided by 7 like that. What did we say we can do to fractions with a square root on it?
So multiply 7 over 7.
You will do that, but hold on one sec. Let's do this first. Let's just take that square root and do it this way. Square root of 4 divided by square root of 7 like that. Does that make sense?
Yeah.
OK. Martin, you with me up here?
Yes.
Keep on top of this one. OK, this is another tricky one because you got the square root inside here. First thing I make it a square root of 4 divided by square root of 7. Then what do? Multiply by
The number of itself.
the number on the bottom square root on both the top and the bottom. Square root of 7 divided by square root of 7. And then what's the square root of 4 times the square root of 7? You can do this, square root of 28 divided by what's square root of 7 times the square root of 7? 7. Okay? So there's your answer. But can we reduce this some more? Yeah. What goes into 28? Square root of 4 times 7 like that divided by 7. Okay? What's the square root of 4? 2 times the square root of 7 divided by 7. Now, OK, a little math philosophy here. We started with this number. We started with this. Oh, sorry, I erased it all. I go a little too fast sometimes and erase these things. Sorry about that. It's on tape. I don't know what minute it is. I'll try to find the minute. We started with this number. Is that any more clear than this number? I don't think so, right? I mean, just because it has a square root in the bottom doesn't mean it's any more clear. I looked up why this is the case. Why do we bother teaching you how to do this? Well, it used to be before you had calculators. If you were to try to get a decimal out of this, it's actually much easier to divide a number by a number that's not a radical than it is to divide a number that is a radical. What's doing your calculator? What's radical 7? Square root of 7. Let me think. 2 point something or other? 2.645 dot dot dot. Just keeps going. If you try to by hand divide by that number, it's going to be a pain in the butt, right? If you try to divide by 7, it's much easier. So back when you had to do these hand calculations, they were like, well, if we make it in this form, it makes it easier to do the calculations. Nowadays, we have calculators. I don't know really if it's worth it. It's worth it for 2 reasons. Reason number 1, there's a lot more forms like this than this. If we all make sure we put it in the same form, then it's easier to grade. It's easier to check your answer with a graded answer, et cetera. That's number 1. Number 2, a lot of this stuff is about making your brain figure out how to do things that have a certain order to them. And that's part of this whole class. So keep that in mind. If you ever think, why are we doing this stupid stuff? It's because it's not necessarily because you'll ever do this in real life. Okay? When you were at Shibeli, did you do any of this? Or Arda, did you ever do any of this in real life? No. Okay? But I mean, you will if you're an engineer or if you're a scientist or something like that. You might do some of this stuff. But really, the idea is to make your brain work a little bit. It's like, I don't know, anybody play a sport? Like, OK, what sport do you play? Basketball. Do you ever go to the gym and work out any other muscles besides just playing basketball? Or do you ever go running? Or yeah, we do all those other things because it makes us a better basketball player, right? It's kind of like what we're doing here. I mean, I know none of you guys said you're studying math for like your major or science or whatever, right? But just getting your brain to constantly think about stuff, that helps out with other parts of your thought, especially in college when you've got to do a lot of thinking for other things. So anyway, I'll get off my little soapbox. But that's why I'm making you do this silly stuff. Because it used to be a good reason for it when we had to do hand calculations. Now it's more so that you practice things. OK. And I will try to find that. Did anybody want me to redo that real quickly so that you get it on paper? Be happy to. All right, I won't. If you don't know how to do it, let me know. OK. Let's see. So now I think you can do 11 and 12. Try doing 11 and 12. I'll do those on the board as well. I already did 11 earlier, but I'll do it again. OK, let me write this up real quick, and then I'll be right there. What's your question?
Like that one, like that one that you're about to do. Can you go ahead and just reduce it from right there?
Sure. But you have to multiply both the top and the bottom by square root of 3. Yeah.
Then you get 3 at the bottom and 7 square root of 3.
It's fine. That's a great way to do it. Yeah, you can do it that way. I would do it this way just because it's the same each time. But if you want to reduce it more first, you can. that what you ended up getting?
No.
No, huh? Is that what the answer is, or no? Hang on, did I do it wrong? I might have done it wrong. That is right. Let's see what you did here.
That is 9 times 3 is 27, right?
Uh-huh.
So that would be 9 and 3. And the square root of 9 is 3.
Did I do it wrong? Hang on. Square root of,
9.
yeah, you did it. So, okay. Times, right. When you did 3 times square root of 3, you have to do the top and the bottom by the square root of 3. So what's square root of 3 times square root of 3?
Square root of 3.
It's 3. What's 3 times 3? Forgot to do that
Oh,
part.
9. Okay.
Yeah. Good idea, but you got to remember to do all your math for that one. Okay, this is how we do. Sorry, I should start on this side of the board, shouldn't I? Starting here, 7 divided by square root of 27. I multiply both the top and the bottom by square root of 27. That gives me 7 times square root of 27 divided by 27. Square root of 27 times square root of 27 is just 27. That means it's 7 times the square root of 3 times 9. I'm trying to just reduce this. Divided by 27. 7 times, I'm going to get rid of the 9 here. That becomes 3. 7 times 3 is 21. Square root of 3 divided by 27. And then I reduce 21 27ths. 3 goes into 21 7 times. 3 goes into 27 9 times. There's the answer. There are other ways to do it. Like Chad said, there's a slightly different way to do it, but you got to make sure to do it properly if you do.
21, 27, that's what I guess.
You guys got it?
Yeah.
Awesome. OK. All right. Let me do, how about 12 as well? Oh, no. Did I just erase what people are looking at? No? OK. If I ever grab this and you want me to stop, like not erase it, just yell at me. All right. And it's all on tape, so we can find the answers if we need to. Let's see. 12. Square root of, I'll start over here this time. Be smart about it. Square root of 13 divided by 3. That equals the square root of 13 divided by the square root of 3. Now we can multiply both the top and the bottom by the square root of 3. OK. That equals square root of 13 times 3, which is 39, divided by 3. What goes into 39? 13. Does anything else go into? Does 9 go into 39? No. That's about it, isn't it? 13 and what? 3? Yeah, so that's it. You got to leave it like that. End of story. What happened to the answer key? Is it still over there somewhere? It's got it back there. Jeremy, do you have the answer key back there? What does the thing say the answer to 12 is? Good. OK. All right. OK, let's see. That's that. I think that was probably the first thing that some of you guys might not have seen in a long, 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 long time. Or it didn't come back easy if you had. Okay. Let's take a break. How about we take another 10 minutes? How's that sound? I'll come back at 20 after. That's 12 minutes. OK. Any questions on the sheet at this point? Yeah, question.
15.
Number 15. Let's see. Does this perform the indicated operations? Sure, we can do this one. Square root of 8 divided by 7 plus the square root of 50 divided by 3. OK. This is a good one because it tests your knowledge from a couple different parts we've already done. Adding fractions. Forget about the radical parts for the square root parts for a minute. How do we add two fractions with different denominators? Find the common denominator. What's the common denominator of 7 and 3? 21. So what's 7 times what equals 21? So it's going to be 7 times 3 equals 21. Square root of 8 times 3 is what you have to do on the sorry, 3 times the square root of 8 is what you do on the top. Whatever you do on the bottom, you multiply on the top. Plus 3 times 7 gives you 21. 7 times the square root of 50 gives you the answer. Now, at this point, what you can do is you could see if you can reduce this. Can you reduce this at all? Yes. Yeah, OK. Because before we even reduce that, let's do this. It's going to be 3 square root of 8 plus 7 square root of 50, all divided by 21. There's your answer. But now we can say, oh, we can still do stuff with this and this, right? So let's actually look at this one first. 3 times the square root of 8. What goes into 8? 4 and 2. OK. Plus 7 times the square root of 50. What goes into 50? 2 and 25. OK, divided by 21. And you got to keep everything the whole so you don't lose the steps. OK, which one can we get rid of here? 4. What's the square root of 4? 2. 2 times 3 is 6 square root of 2. Plus, which one can we get rid of here? 25. That's going to be 5 times 7 is 35 square root of 2 divided by 21. Hey, look, can we now add these two because they have the same radical? Now we can. So 6 plus 35 is 41 square root of 2 divided by 21. Does anything go into both 41 and 21? I don't think so. Yeah, I don't think so. Although it looks like it should, doesn't it? But it doesn't. Yeah. So that's your answer, 41 square root of 2 divided by 21. That was a little tricky one, too. These things get a little tricky sometimes. Is that what the answer was on this one? This is 15? 41 square root of 2 over 21. That's right, yeah. OK. You reduced, oh, you could do that. But you can't add them until after you do the common denominators. Yep. But you can do that first. But you would end up with this divided by 7 divided by 3. 7 over here, 3 over here. Yeah. Yeah. It wouldn't be 6 and 35, though. It'd be the, yeah. That's cool. OK. Anything else on this sheet so far? Let's wait on the rest of the sheet. I'll leave this for a sec. Does anybody remember when they were in grade school talking about the distributive property and the commutative property and the associative property and the inverse property? We're going to do all that. And I'm going to make it pretty easy. We're going to do a bunch of examples where you can see these things in action. They are actually very important for when we talk about some more algebra type things, because you use those properties all the time. Okay? Jeremy, can I erase this now?
Yeah.
Thanks. OK. All right. Let's go back and talk about all those numbers that we've been doing so far. I'm going to have a big box here. I'm not going to label the box quite yet. OK? We said we have the natural numbers. We said at the beginning of class those start with what? 1. When we add 0 to it, we've got what numbers? Whole numbers. And notice what I just did. Are the natural numbers inside the whole numbers? They are. OK? If we add the integers to that, can I do this and say that the integers are inside or the whole numbers are inside the integers and the natural numbers are inside there? OK, and then we talked about another box, the rational numbers. OK, are integers rational? They are, because you can always divide by 1 to make it into a fraction if you want. OK, and all these fit into these boxes. Then we said there was a whole other section of numbers over here called the irrationals, like that. OK? All of these numbers fit into one giant box. Anybody know what that's called? The real numbers. Okay? All of those guys fit into the reals. The ones we're not going to talk about are the imaginary numbers, which we're not going to talk about today. Okay? So all of these guys are on that number line we talked about. Okay? What I might ask you to do, in fact, in the homework it says you have to put these into various categories. So let's look at the following numbers. I'll do this in what we call set notation. Don't worry, it just means a little curly bracket. 18, -5, 7/12 pi, 3 times the square root of 2, -4/15. OK, oops. Should be a curly bracket. Let's go through these and figure out which ones are in each category. Which ones of these numbers are the whole numbers? Is 18 a whole number? Check. Is -5? No, it's not, because it doesn't fit in there. It's negative, right? OK. Is 7/12 a whole number? No. Pi? No. 3 radical 2? No. -4/15? No. OK. So the only whole number, I'll put the whole number by this W fits here. OK. Which ones fit in the integers? Is 18? Yep. Integer. How about -5? Integer. How about 7/12? Not an integer. Integers are the counting numbers with negatives. 7/12 isn't an integer, right? You can't reduce it anymore. Pi? No. 3 radical 2? No. -4/15? Nope. How about rational numbers? Is this a rational number? Sure it is. How about -5? Sure. 7/12? It is. Pi? Nope. 3 radical 2? Nope. -4/15? It is a rational number. Irrational. What are the only two irrational numbers on here? Pi, irrational, irrational. OK. You'll have to be able to do that. Put them in categories. It's not that hard. You just got to remember what the categories are. OK. Now, on page 277 in your book, you do not need to go there. I'm saying that so that you can look it up if you want to. They've got a whole bunch of different properties. This is what we're going to do for a few minutes here. We're going to talk about these various properties. OK? I know you're looking at it on the page. Yeah, don't look too hard. It's kind of scary. OK. Can I erase this? Anybody still writing these? OK. All right. Here are these properties of real numbers, the ones we're going to talk about. For addition, the additive properties. Additive properties. In other words, the properties that we talk about. Is that how you spell properties within? Is it IES? Yeah. IES. There we go. Tell I'm not an English major. Additive properties. OK. We've got this property called closure. OK? Closure means if you add two numbers together, OK, those numbers remain real numbers. OK? Real numbers. So if I have a real number and I add a real number to it, is it still a real number? Yes. Sure. That's an easy one. OK? It's called closure. Do this like this. Closure. If you add two numbers together, they're real. That's not a huge big one. The next one's a big, big one. It's called the commutative property. C-O-M-M-U-T-A-T-I-V-E. The commutative property. I'll give you a little way to remember this. But what this means is if you do A plus B, that equals B plus A. What did I do? I just flipped the order. OK? This works for addition. Commutative. Here's the way I remember it. If you're going to commute somewhere, you're going to move. So didn't B move, or A move, and B moved? They commuted, right? That's the way I guess I remember it. OK? Is subtraction commutative? A minus B equals B minus A? Not true. Subtraction is not commutative. Okay, you can't do that. But you can do it with addition. Makes it easy when it makes it good when we're adding different numbers because we can say, aha, I can move them around if we're trying to do some things with it. Another one, this is another real big one, the associative property. The associative property says that if I group two things together, a plus b in parentheses plus c, that equals a plus b plus c with the parentheses like that. Okay? How do I remember this one? Anybody think of a way I might remember that one? They're like friends. They're associating with each other. If you have associates, they like together, right? They know each other together. Associative is you're associating A and B here, and you're associating B and C here. And that's kind of how I remember it. I normally get these two mixed up. If I'm going to get any mixed up, it's going to be these two. Okay? All right. We also have a property called the identity property. We've already used this one. Well, we used it for multiplication. The identity property says 0 plus any number equals that number. Okay? Or it also equals a plus 0. But that's more of an associative thing. Really, it's this. Any number plus 0 equals that number. That's the identity. Okay? Easy enough. By the way, we're going to do the same thing with multiplication in a minute. Okay? We also have the inverse property. The inverse property says a plus negative a equals what? 0. So what's the inverse of 5? Negative 5. The inverse of a is negative a. What's the inverse of negative 12? 12. Okay? All right. Those are our additive properties. I will let you write them all down. Questions on these? Let's do a couple examples. What if I said a plus b plus c plus d equals b plus c plus a plus d? Which property am I using there? Commutative, because they're commuting around. They're moving, right? Okay. What if I said a plus b plus c in parentheses plus d equals a plus b plus c plus d in parentheses? Associative. I'm associating them differently. Okay? Same sort of thing. Okay, that's the associative property. 5 plus 0 equals 5. What property is that?
Identity.
Identity. It's the identity. You're getting your same number back. Okay? If I add 72 and the square root of 3, do I still get a number that's a real number? Are you sure? What did I say? 72 plus the square root of 3. Is that still? Can I still find that number somewhere on the number line? Sure, I could. I would have to know what that is in decimal form and add it to this, but I could still find it on the number line. That's the closure property. I'm not going to worry so much about this one. This one's not as important for what we're doing. Okay. All right. Can I erase these? I'm going to put we did the addition ones. Let's do the multiplication ones. Okay. In fact, I'm going to make it easier on me. This is what's nice when you have a board. I'm going to leave all the numbers. I'm going to leave most of the stuff up there. You guys have to write them all down again. Multiplicative. Did I say multiplicative? How about we just say, yeah, multiplicative, I guess. Multiplicative. A-T-I-V-E. Multiplicative. In other words, the properties for multiplication. Silly English word, multiplicative. OK. Look back in your notes for the addition one. If we add two numbers, do they remain real numbers? What would be the similar rule for multiplying? If you multiply two numbers, are they still real? They are. That's the multiplicative closure rule. Commutative. Before we added things together, A, B, C, or I'll just do AB for now. AB equals, to commute them, what would we do? Yeah, BA. Is that still true? Is 5 times 2 equal to 2 times 5? Sure it is. That's the commutative rule. Associative rule. Before we said A plus B plus C and had the parentheses around that, can I do A times B in parentheses C equals A times B times C? Yep, that's the associative rule. We're just associating A and B together, or B and C, and multiplying them all together. Again, these rules don't work for division or subtraction, but they work for addition, and in this case, the multiplicative ones for multiplication. OK, somebody, think about this for a sec. What's the identity for multiplication?
Times 1.
There we go. 1, well, let's do it this way. Yeah, I guess 1 times A equals A. Or you could say A times 1 equals A. That's the identity. Because any number times 1 gives you the number right back again. Okay? All right. What would the inverse property for multiplication be? This is one where, well, I guess before we used negatives, so what's the inverse property for multiplication? What times something will give you the identity of 1? A times what gives you 1?
Itself.
Nope. A times A gives you A squared. A times what? 5 times what gives you 1? 5x equals 1. X equals 1/5. So A times 1 divided by A is the answer. OK? So A times 1 divided by A equals 1. What's the one thing we can't do?
0.
Yeah, if A is not equal to 0. So we have to say it. We have to say A is not equal to 0, because you can't get an inverse of 0, because you can't divide by 0. Okay. All right. So those are the big ones for addition and multiplication. Was that so hard? You probably spent like 6 weeks in elementary school learning that. Right? This isn't too bad, because we know enough about numbers now. There's one more property which is really important, super duper important, and we'll get to it later. People still writing this? OK, let me erase some of this. Actually, I'm going to erase all of it right now. There's one more property that we have to talk about that, as I said, it's super duper important. And it has to do with multiplication and division. OK? It's called the distributive property. Distributive property. OK? And what that means is, and we're going to do some examples here with real numbers. A times B plus C equals, anybody remember what this one is? A times B plus A times C. In other words, the A distributes across the B and the C. It's distributed to both B and C. Some people mess this up and they try to do like AB plus BC or something like that. It's whatever on the outside, whatever being multiplied gets multiplied to both parts of the inside. OK? So let's see. 7 times the square root of 2 plus 8 equals what? Using the distributive property. 7 times the square root of 2 plus 7 times 8, 56. I don't think you can You can't make that any more simple. You can't simplify it anymore, rather. Okay, but did you see how we distributed the 7 through? Okay, that one's pretty important. Okay, let's try some other examples here. Let's see. How about this? You tell me what property it is. 3 times the square root of 5 plus 4 equals, oh, I think my pen's running out, equals 3 times the square root of 5 plus 12. That was silly of me to start with that one. It's the same. Why did I do that? All right. Aha, that was right there. OK. How about this? 2 times 3 equals 3 times 2. Commutative of which property? Multiplication, because we're multiplying. Good. OK. How about 1 times 3 equals 3? Good. Identity of multiplication. Good. OK. How about this one? 1/2 plus, parentheses, square root of 17 plus 4 equals 1/2 plus the square root of 17, in parentheses, plus 4. Associative of addition in this case. OK. And then one more. -3 times -1/3 gives you 1. What's that one? Inverse for multiplication. OK? These so bad? These aren't too bad. I don't think these things are too bad. But you do need to know those. And they're going to be really important, especially distributive one, and especially commutative one and associative. Those are the 3 biggies that are going to make a big difference. We're going to use this one a lot, although I'm not really going to say it's the identity. Well, yeah, we're going to use this one a fair amount of time. We're going to use, the inverse. We're going to use the identity one a lot when we already did earlier, square root of 17 divided by square root of 2, where we multiply both sides, or the top and the bottom, by the square root of 2. Square root of 2 over square root of 2, right? That's where we're going to do square root. This is which property? 17 over square root of 2 times 1. Which property is that one? Identity for multiplication, because that equals 1. And, by the way, which property is this to equal 1? Isn't that it right there? You're really multiplying square root of 2 times 1 divided by the square root of 2. Isn't that what this really means? Yeah. So you use 2 properties, which we now talk about in this example. The inverse, well, the inverse property and the fact that you're multiplying by 1, the identity. Let's finish this up while we're doing it. What's on the bottom here? 2. What's on the top? 17 times 2, it's 34, square root of 34. Do any factors go into 34? Let's see, 8, no, 4, no, 2, 17 and 2, so we can't reduce that anymore. Yeah. OK, good. All right, so that was actually 2 whole sections right there. We have, on your sheet, you've still got some other examples here. So let's finish up these 2 sheets. And then I've got one, because you guys said you loved word problems so much, I've got some word problems to do too. Oh, thanks very much. Thanks. So for right now, work on these. When you get them done, we'll take a look at the word problems.